Okay.
She might, I don't think she'll get an A in this first test, but she might get a D.
Yeah. Okay, well, let's talk about what we're doing today in this class. I got this book. Let me get my book. We're just about done with this chapter we're in. Okay, so let's take a look at this. Let's put our input onto PC so that we're seeing the PC. All right, so today we are going to, looks like we're going to finish up chapter, oh, that's not updated now. Oh, yeah, it is. Today is the 27th, so we're finishing up chapter 5, 5.3. Excuse me. And this is another design example, robotic arm on a space shuttle. So we're going to take a look at the different things going on there. And then we're going to talk about our project that will start next week. It will start on Monday. And we'll probably go for at least next week, probably into the week after that. A little bit more complex of a problem than we did with the bridge project. But the idea is still the same. We're going to use materials that are in your building kit, and we're going to have some specifications, some goals that we're going to try to meet, and some specifications that we have to follow, design specs, and parameters, and so on and so forth. So, space shuttle. Right? It's kind of a thing of the past now that they've canceled the space shuttle program, but the space program is not a thing of the past, so they still use several things like this. So here you have a picture of the space shuttle. It's upside down, obviously, and you have this robotic arm that's coming out of it, and it's got a grappler on it, a kind of a hand on it that can clamp onto things and move things around and manipulate things. They used this robotic arm to launch satellites, to construct things in space, to work on the space station, on the Hubble Space Telescope. They even had a fitting so that you could put an astronaut on the robotic arm and they could go out and do work that way. But remember that we need to have some properties that are important to us, or that we think are important. We need to have them listed, and then we need to evaluate how important they are relative to other things that we're going to make part of our project, right? So here is our list on page 138. We have a list of 1, 2, 3, 4, 5, 6, 7, 8, 9 things. 9 properties that we want this robotic arm to have. We have a weighting factor for each of these properties, and we have an explanation of these properties, right? Soft grip, that's really important. It's a 10 on the weighting factor. Failure does not damage space station or shuttle. So if it fails, there needs to be some kind of safety mechanism that doesn't make it break anything, right? It needs to be energy efficient, mass, reliability, full temperature range, compatible with vacuum, cost, time schedule. So all these things here have a weighting factor or a ranking. You could think of it as how important they are. 10 being the most important, 0 being the least important, of course, or 1. And then they explain why they've weighted these things the way they do and why they think they're important, right? It's an important part of the design process to understand what your design needs to have in it and how important those needs are, right? So the things that are 10s take precedence over the things that are 5s or 9s or 7s or 6s or whatever else, right? So you put together your design team. Of course, you're going to have people that are going to specialize in certain things, people that are going to oversee many things. You're going to have engineers, you're going to have designers, you're going to have maybe people that are involved with stuff outside of engineering. Like on the previous one with the paperclip, we had marketers, right? Probably not going to have a marketer for this, but we might have a NASA representative to explain to people at NASA what's going on and to be in contact with them to communicate back and forth with NASA or whoever else, with the other companies that are doing this. So we've got all these very basic properties, but we don't have specifications, like what is the temperature range right here. It says compatible with vacuum, operates over full temperature range, right? We don't know what that full temperature range is, and so maybe we need to write some things down that are specifics about that. And that's what we do in step 3. We identify the constraints and the criteria, which essentially means we give all the details and the numbers and all the stuff that make this stuff doable, so we know what that actually means technically, right? Then we start to search for solutions. We start to brainstorm, right? We sit down in a group and we talk about all the possible ideas and we throw out any crazy thing we can think of. We make little sketches. We make lists of things. We maybe search the internet for people, things that have been done before and get ideas that way. We bounce ideas off each other, whatever it is we do. And maybe we find that there are 2 different robotic hands from our brainstorming session that we think are the best ideas. One of them being a cantilever design here, like this, where you have a cable running up here to an actuator, which would be connected to some kind of hydraulic or motor or something, and this would be pulled this way, and by pulling it that way, you would open up this clamp, and by releasing it, it would clamp down on this, and you would be good to go. Or you could have this one here, which has a fixed arm on this side, and it has this arm here that's on a pivot on this side with your pneumatic or hydraulic actuator there. And they show 2 different pictures of this so that you can see that there's a 1 claw in between the other 2 claws and so on and so forth. So they kind of whittled it down and got rid of all the bad ideas or the ideas that were not going to work out so well, or maybe were not very feasible, ideas that couldn't work because of cost or time, or we didn't have the right materials, or they're just too complicated or whatever else. We kind of whittle it down to these really 2 good options, and we're good. They actually have 3 options in the writing here. Oh, here's the next option. Oh, no, that's not. They have 3 options for the actuators. So the actuators are the actual things that make the hand open and close. And they have 3 options for the actuators. And here they show the different options for the actuators. And this one here, we have... This option here is mostly an electronic option, so they've got an electrical diagram here. This one here is a pneumatic option. Or it might be using pneumatics, which is air pressure, or but also might be using hydraulics, fluid pressure, oil pressure, where you have valves and a piston with with a rod in it. And then this bottom one uses springs to actuate things. Actually, this one uses an electric motor and springs. The top one is actually pneumatic. That's the thing I misunderstood. This top one is actually pneumatic. This middle one is hydraulic, and the bottom one is electric. And they're going to talk about the different advantages and disadvantages, and they're going to start to evaluate these 3 different ideas. So how do you evaluate? You go back to this idea of the evaluation matrix. We have option A, option B, option C, And we have all those properties that we talked about over here on the left. The soft grip, the failure does not damage space station, and so on and so forth, all 9 of those things. And their weighting factors. And then they scored each one of the options on a scale of 1 to 10. So the first one, which was the pneumatic, or was the pneumatic one, I believe. The first one, which was a pneumatic one, got a 10 for soft grip, and they got a 1 for energy efficient. So you take that 10 for soft grip and you multiply it by 10 because it has, the soft grip has an important, it's very important. It has a high weighting factor. Multiply it by 10 to give it a weighted score of 100. And it turns out all 3 of the options got a weighted score of 100 on that. But if you go down here to its score for energy efficiency, a 1, it has a weighting factor of 5. Multiplied by 5, it only got 5 points there. And option B got 25 points, and option C got 50 points. So far, option C is winning. And it turns out in the end that option C wins all the way down the board with a total score for option C of 630 versus 370 and 425. So they choose option C to be the best idea because of all the advantages that it has over the others, right? They outweigh them using this evaluation matrix. So that is how that's in a nutshell, in a very short, non-detailed way, how you go through this design process. Right? You have a problem, you begin to flesh out all of the details of that problem. You start to rank the importances of the different parts of the problem in your table of properties, like this table here where we listed our properties of the solution that we're going to try to choose. And then you start brainstorming solutions, you start comparing solutions, you do an evaluation matrix with your best solutions, and then you're going to have a place to start. That gives you a place to start on actually building, putting together a prototype, testing it, redesigning, and so on. Which is where we get to at this point. So, now let's take a look at our project and see how we can apply these things apply these skills and this knowledge to our next project. So our next activity is all about motion, but not about fast motion, it's about slow motion. We want to do this problem, this one right here, and I will send this out to you. This one comes from the University of Arkansas. I thought it was an interesting problem here. Page 23 is where we want to go. It's over here. So what is the problem, the scenario, right? We've got this thing where we want to build something, some moving object that will travel, that will move from one point to another, but will do it at the slowest possible pace, right? So the materials that I've given you are the materials in your build kit, and you'll notice that in your build kit there are more than just wood sticks and dowels. There's lots of gears, there's wheels, there's pulleys, there's rubber bands, there's lots of little screws and other things like that in there. And so this is a little more complicated. It's going to be a rubber band powered vehicle. You have to use the rubber bands in some way to make it move, but you want to make it move as slowly as possible. Now the wheels that are in your kit are the kind, they're red and about 3 inches across, and there's some big, thick, wide rubber bands that are used for the tires so the wheels don't slip. However, if your wheels slip, your car may actually move a little bit slower. But having the weight on your wheels will actually move it a little bit slower too, the weight of the rubber bands. So it kind of depends on how you want to design that. But here are the design criteria. Our problem is to get a car that'll move very, very slowly across a certain distance. Here they say about on a distance, across a distance without falling from an elevated table surface. I'm just going to give you a distance like 1 yard, 3 feet or something like that. But here are your design criteria. These are the things that your car should be able to do. And you have to decide which things are most important, maybe decide your best design from, weighting these things and scoring different designs that you come up with, that you think about. But you're going to use only materials and tools supplied at the beginning of the challenge. So you've got your tools, you've got your toolkits. Completed vehicle must operate freely without human intervention once it starts the test. You may not alter the testing platform in any way. So it's got to be the distance I say and nothing else. The completed vehicle must remain in motion during the testing phase. It cannot stop for more than 1 second. If a vehicle falls from the testing platform, so in other words, if it leaves the area of the test, which will probably be like a 3 foot by 3 foot square, then your test will be over essentially. Teams will have 3 trials on the testing platform. So the best score, or your longest time rather, will be your final score. Teams will not be allowed to make significant modifications during the testing. We'll have 3 minutes between trials. And so if something breaks, you can fix it, you can put it back together, but you can't really change your design. Teams will be required to submit vehicle sketches prior to testing. Okay? So we're not stepping you through each step of the design process in this problem. So you're going to have a little bit more. You're going to have a little bit more freedom to go through the process the way that you want to. But one of the things that I'm going to require is that you send me a design, a drawn out design with specifications, with measurements, kind of like we did with your bridge. I want to know the materials that you're going to use, where you're going to use them, how you're going to use them, and I want it drawn out in very specific detail. You're probably going to have to give me 3 drawings, one from the side, one from the top, and one from the front or back, so that I have a complete idea of what you're doing with your vehicle. Here they give us the list of materials, and I actually did not include all of these materials in your kit. You have wood, you don't have straws, and I have a bunch of straws, so if you need them I can get them to you, but you can also just get them from McDonald's or wherever else. Balloons I do not believe I included as well because I ran out. I did give you rubber bands. I gave you some things that are like tongue depressors, not quite the same size. I'm not sure what size wood I gave you, but if you need some tongue depressors, you can get some from a local doctor or dentist or something, or you can email me and I'll send you some. Wheels and axles I gave to you. Paper and cardboard stock I gave to you. I didn't give mouse traps or electric motors because I'm not including mouse traps or electric motors or batteries in this test. So you're going to use rubber bands to power your car. You decide how you're going to do that. But we're going to do rubber bands. But I did give you an assortment of gears, and so you can use gears to slow down the car. You can use masking tape of any kind that you have. I didn't include that. You can use whatever kind of glue you need to use. And then, of course, you're going to use a stopwatch, a yardstick or 2, and videotape when you test your vehicle and turn in your test. Right? Again, this is talked about. They talk about this in teams, but since we're spread out all over the state, we will do it as individuals. So that those who do not have somebody they can work together with, they're not disadvantaged. So you will make your own car and do your own tests. But you definitely need to have a design. So I will send this out to you today, and you will get these instructions. And then next week we will start working on it, so that if you have questions you can come and ask me. I will go through some of the materials next week on Monday, some of the materials on Wednesday, so that you can kind of see how these things work together. And you can learn a little bit about gears, you can learn a little bit about wheels and so on and so forth. Maybe we'll learn a little bit about powering something with rubber bands. So I'll give you different ideas and I'll give you different options to think about. And then you guys will be on your own. On Friday, we'll just essentially not have a class, and you'll be on your own to work on your project and finish it up. However, by next Wednesday is when I want your design drawing, a complete finished design drawing. So you are on your own to start this process, the design process, to decide how you're going to build your car. On Monday, I'll give you some ideas so that you have something to start with. But on Wednesday, I want a drawing of your vehicle that is going to go as slow as it can across a 3-foot expanse. So, having said that, I think we're done. I will send this out. I'll post it up on Blackboard if anybody is using Blackboard, but I'll send it out to your emails directly as well. And if you have any questions, feel free to call, feel free to send an email, whatever you need to do to contact me, and we will help you out in the way we can. So, have a good weekend. We'll see you next Monday.